and gentlemen, we are going to start off today with me actually talking not at all, and you guys doing some practice, because the very last thing that we did was wrap up going through all of the shapes that you are required to know. So what I would suggest is that you take out that chart that I gave you, have that in front of you. For each one of these, what I would like for you to do is to draw it, meaning draw its Lewis structure, tell me its shape, tell me its bond angle, and one more thing that is not written in the instructions here, please tell me whether it is polar or non-polar. Okay? So we'll just take a few minutes. I'm going to walk around and help you if you need help. But this is what we're going to start with today. Go get it. Yep, check these first 5. If there's something up here that you are not sure why I have it, please ask. Yes.
So I probably misunderstood, but I thought that all linear did not.
Okay, great question. This first one right here. Most linear structures are nonpolar, but that's only because most of the compounds that we're dealing with have the same element as the terminal atom, but in this case the terminal atoms are not the same element, so that makes the molecule unbalanced, automatically polar. Okay, and that goes for any shape. If the terminal atoms are not the same element, automatically polar. Okay. Okay, here's the second set. This was the second column. Check them. So let me say something about this one in particular. Okay, some of you may have this drawn with a double bond and a double bond. Okay, some of you may even have it drawn with a triple bond on this side and a single bond on that side. Okay. Would I just immediately expect you to know which one is the correct one? No, probably not. If I wanted to be really tough on you, though, I could expect you to draw the correct one based on something we talked about last class. Formal charge. Okay? There's 3 ways to draw this. And there's a little bit of a catch here. If you drew all 3 out, triple, single, double, double, single, triple, 2 of the structures have the same number of formal charges of 0. And just to review from last class, that's how you decide which structure is the better one, is which one has more formal charges of 0. Okay? And I'll have to go back and look at my notes, but I think that this one and having double-double will both of those structures will give you the same number of zeros for formal charges. So technically, either one of those would be fine. Okay? But I'll go back and look at my notes. This one may be better, but I'll go back and double-check. Okay? But in general, I would accept this one. I would accept double-double. Okay. All right. Let's move on. Okay. So, guys, the final big topic when we're describing molecules, we've drawn them, we've predicted shape. The final topic is something called hybridization. Okay, and let's just think for a second, hybrid. What does that word mean? I mean, you hear it in biology when you do dihybrid crosses and you know, when you have a hybrid car, what does the word hybrid mean? Yeah, you're blending or mixing two things, two ideas, two concepts together. I mean, a hybrid car is called a hybrid car because you're blending power from gasoline and power from an electric battery, okay? What we're blending here is atomic orbitals. We're blending different types of orbitals. And the reason we're doing that is the reason behind so many processes in chemistry is to attain a minimum energy, a minimum potential energy. And those of you that go on further and further in chemistry will hear again and again that that is the reason behind so many things, is to achieve minimum energy. Okay? And to illustrate this point, okay, I'm going to use the molecule methane as an example. Okay, now don't just blindly start copying all of this down. Just listen and write things down as they come. Okay, but I'm going to draw methane on the board. We've used it, we've seen it multiple times. Has that tetrahedral shape. And if you would, look on your periodic table and tell me, how many valence electrons does carbon have? You got it. 4 valence electrons. Two of them are in 2s, and the other 2 are in 2p. Okay, well, first problem here is, well, tell me this first. Okay, if you look at a Lewis structure, let's just refresh my memory here. Anytime we draw a line like that, what is that really representing? Okay, a shared pair of electrons. That implies that one electron is coming from carbon and the other is coming from hydrogen. Well, that implies that I have 4 available electrons to pair up. And if you will look at how this is drawn, this orbital notation, this kind of looks to me like carbon only has 2 electrons available to pair up. I mean, these are already paired with each other. So the first part of this story here is, and I've said this before and I'm going to say it again, electrons are not locked in place. Electrons can move wherever they are needed, and that's exactly what happens here. Okay? This electron doesn't stay in 2s. It jumps over here to 2p. Okay, so that's the first part of the story. Doesn't it now look like carbon can pair up with 4 different things? Yes, it can. Okay. Here's really the essence of hybridization right here. True or false? These 4 bonds in methane are identical. True or false? True. I'm not trying to trick you. These are identical. Okay. Let's think back to something that we didn't talk about a lot, but we did talk about a little bit. The shape of these orbitals. Do you guys remember vaguely that we said that s orbitals have a spherical shape and p orbitals have what's called a dumbbell shape? Okay, well, let me come back over here. These bonds are identical, true or false? True, they are. Are these 4 shapes identical?
False.
No, they aren't. Well, they must be. So how do we turn this into 4 identical shapes? By blending these shapes. And this is what it looks like. If you take a sphere and 3 dumbbells and mush them together and then spread them back out to get 4 identical things, this is what you get. Are these 4 shapes identical? Yes. Okay. Here's that tetrahedral shape right there. Okay. This is hybridization. Are you going to be asked to draw this out? No. All right. What you will be asked is look at this Lewis structure. Tell me what is its hybridization. And what is it? It's sp3 hybridized. That's how you say it. You say methane either has sp3 hybridization, or you can say it's sp3 hybridized. Okay? And you guys will notice on that VSEPR chart that I gave you last class, there is a column in that chart that says hybridization. And if you look next to tetrahedral, it'll say sp3. Okay? And it's not just for shape purposes also. Okay? Do we need 4 identical shapes? Yes. It's also for energy purposes. We need these bonds. These bonds have identical bond energy. So we blend them, hybridize them, so that we get 4 identical bond energies as well. So it's for shape reasons, it's also for energy reasons. Okay? And the way I'm saying this is not great. You know, why do we blend these things? There's not like some magical wizard that's saying, well, we're going to put these together. This is how it exists in nature. Okay. Now, I'm going to draw some other things up here on the board. Some Lewis structures that you should be very familiar with because we've worked with them a lot. We've got methane. Here's another one that we've seen many times. What's the name of that compound? Ammonia. And water, okay? I want you to look at these 3 Lewis structures. Besides the fact that they all have hydrogen as the terminal element, besides that fact, what do these 3 structures have in common, particularly around the central atom? Something they have in common. They have the same, thank you, that's the term I was looking for. They all have the same steric number. What is their steric number, all 3 of them? 4. All of them have a steric number of 4. Okay? Do they all have the same shape? No. This is tetrahedral. What's this? Trigonal what? Trigonal pyramidal. What's this? Bent. Different shape, but they all have the steric number. Well, guess what? Here's the good news. Hybridization is dependent upon not shape. It is only dependent upon steric number. All of these have a steric number of 4, so guess what? They all have sp3 hybridization. Okay? Steric number of 4. All of them. So, how many hybridized orbitals do we need? We need one s, p1, p2, p3. sp3 hybridization. And you'll notice on your VSEPR chart, everything in that steric number of 4 family, they all have the same hybridization. Okay? let's look at another example. Okay. Don't worry about this entire structure. Focus. Yeah. Focus on this carbon right here. Okay. You guys tell me, what's the steric number around that carbon? Not 4, 3. Okay. Remember, steric number is like how many sides have something off of it. Multiple bonds count. When we're counting steric number, they count like a single bond. So, steric number of 3. I don't need 4 identical shapes like I did on the last example. This time I only need 3. So let's come back over here. We're still dealing with carbon. I need 3 identical shapes. And you might say, oh, well, that's perfect. Why don't we use these 3 since these are already the same shape? Well, that would be really nice, but that's just not how nature has decided it's going to do it. So, which 3 do we choose? We choose this one, and this one. So this carbon is not sp3 hybridized. It's sp2 hybridized. I am not forgetting about this extra one. He has a role to play. I'll come back. Okay. But guys, again, hybridization is based on steric number only. This has a steric number of 3, S, P1, P2. Okay? This is sp2 hybridized. And let's just see what that looks like. Okay, so we blend 1 s orbital, 2 p's. We get our 3 blended hybridized orbitals. There's that trigonal planar shape. What's the bond angle on this guy? 120. Very good. Okay. It's also for energy reasons. We have 3 hybridized orbitals of that hybrid, that blended bond energy, but we have this extra one. What happens with that? Well, I will show you. Okay. Let me help you get your bearings here, because sometimes these 3-dimensional drawings can be really tough to visualize. So remember that the whole molecule looked like this. We had 2 carbons, 4 hydrogens. Okay. And let me in fact draw in just to help you a little bit more. There's a hydrogen there, a hydrogen in the front. Okay. So if you look at just these purple pieces here, can you see that trigonal planar shape, that 120 bond angle? Okay. So here are the hybridized orbitals. What this pink thing is, guys, remember I have this extra electron in an orbital that is not being hybridized. And it is my understanding that this extra electron is essentially doing a figure 8 constantly above and below the plane of this molecule. What does the word planar mean again? Flat. Trigonal planar. The hydrogen atoms and the carbon atoms are all on one flat plane. And this extra electron for the carbon on this side is going up and down and up and down and up and down and up and down and so on and so forth. Well, this carbon has an extra electron too. And it's doing the same thing. So I have a pair of extra electrons here. And ladies and gentlemen, when you have a pair, not one, but a pair of unhybridized orbitals, one is coming from this carbon, the other is coming from this carbon. When you have a pair of unhybridized orbitals, that is something called a pi bond. Not pi like apple pie, pi like the Greek letter pi. Okay, now this is the definition from your textbook. I'm not crazy about it. I would prefer to say that a pi bond is, as I just said, formed from a pair of unhybridized orbitals. And why your textbook chooses to draw a pi bond as like an eraser with legs and its reflection, I don't know why they draw it like that. But this symbol is supposed to represent a pi bond. I don't know. The other type of bond, which comes from hybridized orbitals, those are called sigma bonds. Okay? Sigma bonds come from hybridized orbitals. If you are feeling a little confused at this point, don't fret. Let me show you how simple your task really will be when it comes to sigma and pi bonds. Let me just pull up a blank sheet here. Okay, I'm going to draw a molecule that's totally nonsense. I'm going to use element symbols that are not real element symbols, like, let me change colors here. X is triple bonded to Y, which is got a lone pair, and that's single bonded to R, which is double bonded to Z, Q, and single bond. What's another letter? J. Okay. Your responsibility for sigma and pi will be to look at a structure and simply count how many sigma bonds are in there, how many pi bonds are in there. Okay. Well, let's start with a simple one and then we'll come back to this guy. Come over here. Alright? I'm just going to, just temporarily, I'm just going to erase that second bond there. Just for a second. How many sigma bonds does this have? 1, 2, 3, 4, 5. 5 sigma bonds. Now I'm going to put that extra bond back. It has 1 pi bond. What I'm trying to say here is, guys, a double bond is 1 sigma bond and 1 pi bond. Yes. Okay. A triple bond is 1 sigma and 2 pi. Okay. So a double bond is 1 sigma, 1 pi. A triple is 1 sigma, 2 pi. So, if you would please, look at this total drawing. How many sigma bonds are there? There are 5 sigma bonds. Okay, if we went through and counted them, 1, 2, 3, 4, 5. How many pi bonds are there?
4.
Okay. 1, 2, 3, 4. 4 pi. Okay. You can handle that, right? That's the extent of what you're going to need to explain. You're not going to have to draw the erasers with legs or anything like that. Okay. But if you put the whole thing together, which I would not expect you to draw this, this is what it would look like, okay? Your carbons, these blue things, these are the hydrogens, all right? Sigma bond, sigma bond, sigma bond, sigma bond, sigma bond, pi bond, okay? The only other thing, guys, that I want to stress that is important about pi bonds is that they do not exist in the same plane as the rest of the molecule. They are perpendicular to the rest of the molecule. Okay? So your knowledge is, can you count sigma and pi bonds and know that pi bonds are not in the same plane as the rest of the molecule? Okay? All right, let's do one more example. Tell me, please, what's the steric number around the carbon in the center? 2. So how many hybridized orbitals do I need? I only need 2 this time. So this is just sp hybridization. Now, that leaves not just 1 extra electron, but 2. In that previous example, what did that extra electron go to create? What did it create? A pi bond. Well, if 1 creates 1 pi bond, I've got 2. This is going to create 2 pi bonds. Don't you see 2 pi bonds? I do. Yeah. Okay? I'm not making this stuff up. Right? So we get 2 hybridized orbitals, 2 unhybridized orbitals. And this is what it looks like all together. I'm not going to ask you to draw that, so don't panic. All right? 1 sigma bond, 2 sigma bonds, 1 pi bond, a second pi bond. Now, instead of having you do a new set of practice, what I thought we would do instead is go back to the practice we did right at the beginning of class, and let's just go through it together and talk about hybridization. Okay? So tell me one more time, hybridization is dependent upon what in your VSEPR chart here? Steric number only. What is the steric number of this first molecule? 2. So what's the hybridization? SP. SP. Just SP. Okay. What's the steric number around this phosphorus? 4. So hybridization? SP3. It has a steric number of 4. S, P1, P2, P3. How about this guy? What's the hybridization? SP3. This one? SP3. What's the steric number around this guy? What's the steric number? 6. Okay? There's no such thing as SP4, SP5. If you will look on your VSEPR chart, on the back where those extended shapes are, you will see hybridizations that go into the d orbital. Are you ready for good news? You're not responsible for any of the hybridizations on this back side of this chart. Okay? Here is the thing. These hybridizations, like sp3d, sp3d2, those are sort of theoretical hybridizations, and it used to be on the AP exam. But research has not been able to find that this type of hybridization actually exists. So it has been taken off the AP exam. You have to know hybridizations for the basic shapes, but for the extended ones, you can just scribble through this column. So I won't ask you the hybridization of this. Or that. What would be the hybridization for this carbon right here?
SP,
SP, this nitrogen,
SP,
this carbon.
SP2,
SP2, this nitrogen.
SP,
SP2. Steric number of 3. Okay. Now, there is something here. You know, when we are looking at shape, we always look at the central atom. But guys, I want you to be aware, I could ask you the hybridization around any atom I want. Like this sulfur. What is the hybridization around that sulfur? sp3. 4 sides occupied. How about this oxygen right here? sp2. Okay. Just to make sure you've got this. How many sigma bonds in this molecule right here? 3. How many pi?
1,
Okay. How many sigma in this one?
2,
How many pi?
2,
How many sigma in this one?
5,
5. How many pi? 0. Okay, good. You got it. Okay. Now, actually, let me come back here. We have already talked about resonance. So what I'm going to go over here, guys, is almost entirely review. Okay? I'm just going to, oops, I don't like that color. I'm going to draw an example of resonance that we looked at last class. The only reason I'm bringing it up again is because we now have some new vocabulary that we can add to our discussion of resonance. So I've just drawn nitrite. Now I'm drawing nitrate. Okay. And I gave you this exact example last class. And we said that both of these have resonance to them, okay? Nitrite, how many total resonance structures does nitrite have? 2. How about nitrate? 3. Okay. And remember, guys, we are still in this time where it's all about how to answer a question on free response with the right vocabulary and the right buzz phrase and everything. What did we say? What was the vocabulary? How do you describe this extra pair of electrons that can move locations? There's multiple ways to say it. Okay, you can say a resonating pair of electrons. What was the slightly fancier word? You could call it a delocalized pair of electrons. We now have a third way of saying it. Are you ready? Get excited. You can call it a resonating pi bond, because that's what it is. The pair of electrons that can be in alternate locations is a pi bond. Okay? So let's talk through this one more time. And I love this question. I love this question. Are you picking up the hint here? It's a great question, this one that I'm about to ask you. It ties in multiple topics into one question. I love it. And I'm going to ask a slightly different question than I did last class. Nitrite versus nitrate. Which one has the longer average bond length? Nitrite versus nitrate, which one has the longer average bond length? Okay? You're in free response. And you're supposed to answer this in 2 sentences or less. First of all, don't shoot the messenger. How many total Lewis structures do you have to draw to perfectly answer this question? 5. Yuck. Okay. Well, guess what? Lewis structures do not count towards your 2 sentences or less. Okay? I always like to start by saying something they have in common, you know? Although they both have, let's be fancy, although they both have a resonating pi bond, they do, this one, you guys tell me, this one has a bond order equal to what? 1.5. Nitrate, however, has a bond order equal to what? 1 1/3. Don't use fractions, write out a number, okay? So although they both have a resonating pi bond, nitrite has a bond order of 1.5, while nitrate has a bond order of 1.33. So this one is closer to the length of a single bond. What's the answer here, by the way? Which one has the longer average bond length? Nitrite or nitrate? Nitrate. So even though they both have a resonating pi bond, this has a bond order of 1.5. See ya. This has a bond order of 1.33, which is closer to the length of a single bond. That's how I would say it. So the only reason I'm bringing this up here is because we have the word pi bond, the words pi bond now in our vocabulary. Do you remember, what does the word delocalized, what does that even mean? Delocalized. Can move around. So what does localized mean? Can't move around. Pi bonds are delocalized. Sigma bonds are localized. They don't move around. There is one very small final topic, and in all honesty, this is more of a physics concept. So please don't ask me follow-up questions, because the answer will be go ask a physics teacher. All right? The reason I personally think that it gets thrown in to our course, AP Chem, as opposed to AP Physics, is because the word electrons is used, and I think, you know, they see the word electrons and they're like, oh, that's chemistry, get out, go, we can't have that in physics, get out. Okay? And it seems kind of oddly placed in this chapter, but whatever, here it is, it's quick. You guys may or may not be aware that there are certain elements out there that are naturally magnetic. Like, you find it in nature, it is magnetic. Do you know one? It's very common. You use it in your everyday life. Or you come across it every day in life. It's the most common building material. Iron. Iron is a naturally magnetic element. Now, there are other elements that can be induced to be magnetic. And then there are elements that no matter what you do to them, they're never going to be magnetic. Okay? The term paramagnetism, paramagnetic elements would be elements that are either naturally magnetic or can be induced to become so. And guys, magnetism of elements is a consequence of unpaired electrons. If you have an element that has even one unpaired electron, we would describe it as paramagnetic. If an element has all of its electrons all paired up, we would describe it as diamagnetic. Okay, like dimagnetism. It is my understanding that that means essentially, and maybe I'm oversimplifying it, like cannot be induced, is not magnetic. Okay, so let's look at our periodic table. This is very quick. Okay, we'll just do these together. Look at where magnesium is, please. Tell me, how many valence electrons does magnesium have?
2.
2. Okay. Are those paired up? Yeah. Well, those are just its valence. What about all of its core electrons? Are they all paired up? Yeah. So magnesium is all paired up. That, ladies and gentlemen, means it is a diamagnetic element. How about bromine? Look at where bromine is on your periodic table. Does bromine have any unpaired electrons? Yes, it does. It only has one, but that's all it takes. Bromine would be a paramagnetic element. Okay. Do you guys know what that is? CD, what element that is?
Cadmium.
Cadmium. Okay. It's just below zinc in your transition metals. What do you guys think?
2.
Well, para or dia?
Di.
Dia. Everybody's all paired up. Okay. Nitrogen. Look at where it is. Para or dia? Para. Has some unpaired electrons. Krypton. Dia. How about manganese? It's in the first row of your transition metals.
Para.
Why para?
Because it has 5 electrons in the D sublevel.
Thank you.
And none of them are paired up.
Perfect. It has 5 unpaired electrons in the D sublevel. Now D, that's not valence electrons. Those are core electrons, but it's okay. It doesn't matter where they are. If there are any unpaired electrons, it's paramagnetic. So you guys tell me which, let's not even go families, just group number. What groups on our periodic table have everything in it as diamagnetic? Group 2, 12,
18.
and 18. Those 3. Okay? You got it. Ladies and gentlemen, that's all she wrote.